The intermediate value theorem. At first glance, this doesn't really look like it's much work or anything that you have to do, but understanding the intermediate value theorem comes in handy later on. We use this theorem to help prove more useful things. So let's take a moment to dissect what this theorem says and look at a visual that represents it. If f of x is a continuous function, and it's specifically continuous over a closed bounded interval, that's exactly what we're looking at here. These square brackets from a to b represent closed and bounded. So f of x is defined on this closed and bounded interval. The intermediate value theorem says if that's true, then for any real number z between the function outputs at a and b, remember a and b are coming from the values in this closed bounded interval, then this theorem says that there's a number c that's in between a and b, satisfying that the function evaluated at that input is equal to that real number z that we started talking about. Let's take a look at a picture so that we can decode this statement with images to go along with it. We've got some function here, and we're saying that f of x is continuous along this closed bounded interval from a to b. And we can agree that we see that in this image, that the function is nice and smooth and continuous between the values x equals a and x equals b. So we're specifically looking at this interval, this closed bounded interval from a to b. Next it says z can be any real number between f evaluated at a, f evaluated at b. So let's take a look. Here's f evaluated at a, that's the y value of the red point. And then here's f evaluated at b, that's the y value of this blue point. So z is some number between those values. So z is only allowed to be in here. If z is outside of this, then all bets are off. But if z is stuck inside of that range, between f at a and f at b, then I can guarantee that there's a number that lives between a and b on the x-axis that will give me that output. So let's pretend like z is matching up with the gold line that you see. If I pick some number z that is above the f at a line and below the f at b line, so z is definitely between there, then I can guarantee that if I head straight across until I hit my function, that I will be able to find a value c on the x-axis that's between a and b. And if I plug c into my function f, it'll generate the point that I've got shaded in here that is at c, comma, f at c, where that f at c is that z value that we started with. Now again, this kind of seems like, why are we talking about this? But really, there's a lot of great consequences of this theorem. One of the consequences would be, let's think of like a very boring function. And let's pick some closed interval from a to b. If my function output at a is maybe a negative number, and my function output at b is a positive number, this theorem can guarantee that the function has to pass through 0 somewhere between a and b. The only way to move from a negative number to a positive number would be to pass through 0. So the C that we would be looking for is like the x-intercept, the value of the x-intercept, where the output f at C is 0. So this can guarantee that a 0 exists on a function. In fact, our calculators use this as a tool to find max and min on a graph. So if you've ever used like a TI 83, 84, 89, and you ask it to find the max or the min, it's using the intermediate value theorem there, a slightly different version, but it uses it also to find the intercepts. So if you use that search for intercepts function, it's using the intermediate value theorem to say, oh, you went from a negative to a positive, there's got to be a 0 in there somewhere. Or if you went from a positive to a negative, the argument works for that too. But like I said, we're talking about this theorem because we are going to use it to prove other things later on. So for now, I just want to make sure that we understand what the statement is, and we'll touch on this later.